the triple integral section. The ones that are left to do are centers of mass of three-dimensional solids. So you can imagine a sphere or a cuboid or some kind of egg-shaped object in 3D space. And for every single point inside that object, that solid object, there's a density function. So you could have an egg shape where it's quite heavy on the right and light on the left, or whatever it might be. And we want to find the center of mass of that particular 3D object. The formula is that the x coordinate, x bar, is the moment yz over the mass m. Y bar is this guy, and z bar is that guy. And making sure I've written them correctly, because I did get them back to front the first time I wrote them down, is, do you notice that x bar doesn't have an x in it, and y bar doesn't have the y in it, and z bar doesn't have the z in it? So actually, couldn't you create a fourth dimensional object and still find the center of mass of it? Wouldn't it just be called x bar, z bar, y bar, z bar, t bar, right? And that would be four-dimensional space-time. So this idea of center of mass, when you use these moment formulas, it becomes a lot more obvious than it was when it was 2D. Yes, Tom?
So when you're finding the moment, just like before, you know, when you wanted to find the moment around the y, you put the x in. This is just, you're putting in the axis that doesn't exist. Does that keeps carrying through? I think that's what
yes.
said,
so look, if you're finding the moment x, y, z goes in there, the moment x, z, y goes in there, and the moment y, z, x goes in there. And I think that's what you were saying. You notice the formula. And you notice it's the thing times the density function. So one of these questions is massively long, right? And so the types of questions you may get, say in a midterm exam, would be only to set up what the integrals would look like, but not to actually calculate them. So you know the point where I would go dot, 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 dot. That's kind of where I would take that. Because the hardest part is going to be setting up the integral. The triple integrals, for the most part, are just going to be polynomials plugged into things. So first one we're going to have a shot at is question 13. In question 13, you've got a cube, and the cube has this going on. And they've got an A here, but that's fine. It could be 10. Okay. And this is basically your region E. And so if you wanted to see what that might look like, the solid which you're trying to find the center of mass would be, well, that would be A, and this would be A, and this would be A, and it'd go along the bottom, and it would go up, and it'd go down, and it'd go like this, go like that. Hey, that's pretty good. Yeah, pretty happy with that shape. Can you imagine a little cube, A units long? Boom, boom, boom. Now, in this cube, the density function is described as 2x squared plus 2y squared plus 2z squared. And that definitely shows you why I should put strokes through z's, because don't my 2's look like z's? Right, so everything is set up. So how do we calculate the center of mass? Well, the first thing you do is you calculate m. And since well, this is its generic formula. It's a triple integral under the solid E of the density function. In our case, it's going to be x equals 0 to x equals a, y equals 0 to y equals a, z equals 0 to z equals a. The density function is 2x squared plus 2y squared plus 2z squared. And in the order I'm doing it, it's z, y, just made it x. All right, so I'll do this guy first. And I'll just leave the other two over here. I won't write what these guys are. It's just these guys again. I'm just saving time. So with respect to z, you get 2x squared z plus 2y squared z plus 2/3 z cubed, evaluated at 0 and at a, and then you've got the other two guys after that. And you plug in a, you get 2x squared a plus 2y squared a plus 2/3 a cubed. And take away nothing, so I won't bother with that. And we'll do a dy and a dx. And y is going to go from 0 to a, so is x. So we're going to be doing from x equals 0 to x equals a, and I'm going to integrate this with respect to y. So what do I get? I get 2x squared ay. Integrate this term with respect to y, you get 2/3 y cubed a, and this guy with respect to y is 2/3 a cubed y, and y is going to be evaluated from 0 to a, and then you're going to do the x's after they're finished. Right, you plug in y equals a, you get 2x squared a squared. You plug a in here, and you get 2/3 a to the 4. And you plug in a here, and you get 2/3 a to the 4. So it's going to be 2x squared a squared plus 4/3 a to the 4 dx. So you're going to integrate with respect to x, and you're going to get 2/3 x cubed a squared plus 4/3 a to the 4. Don't have that anymore. Evaluated at x equals 0 to x equals a. 2/3 a cubed times a squared plus 4/3. That should have an x in it. There we go. 4/3 a to the 4 times a. Take away a whole load of nothings. That gets me 2/3 a to the 5 plus 4/3 a to the 5, which gets me 6/3 a to the 5. After all that hard work, 2e to the power of 5. So far, so good.
Where'd that negative a come from?
That's not a negative, it just looks like a negative, it's a times. So 4/3 a to the 4x becomes 4/3 a to the 4 times another a, and I got that. So it's just a times, it kind of looked weird. So far, so good. Right, now what you would do next would be, you would have to find, I mean, if I just did this one question, that would be the end. What we'd have to find is this guy, and this guy, right? And then we'd plug them in here, and all the good stuff would get divided. So just for one example, if I wanted to find that one, the moment about the y's, it would be our triple integral y, the density function, dv. Now, when you're doing the moments about y, they're called m of x, z, y fill, and it's going to be 0 to a, 0 to a, 0 to a, and the function that we would be doing it to would be y times, what is that guy I wrote him down a minute ago? Yeah, y times the density function. And you do a dz, a dy, and a dx. And 10 minutes later, I would get an answer, agreed? And then I would, I'm making this up. Let's pretend that the answer just happened to be 4a squared. Now make it 4a cubed, right? Then if you wanted to find y bar, you get it by doing that. So you do 4a cubed over, was it 2a to the 4 I got earlier? Yeah, 2a to the 5. And that would come out as 2 over a squared. And that would be the y coordinate of the center of mass. Now I'm going to do a little cheat here. Although that isn't correct because I didn't calculate that. If I had calculated that correctly, that would be the middle term. What could I do about the other two answers? I could write them down right now.
Symmetry.
Yeah. Would you agree that because the density function is symmetric and that this was a symmetric limits, right? It was a box, a cuboid, that symmetry would take over. So if you saw a question, well, actually, now we've done that one. Once you get the real answer for this one, can't you just duplicate it and it'll save you a big load of work because of symmetry? So there is a lot of steps to calculate the center of mass. But once you've set up the region E, once you've found the limits of integration of E, it becomes a lot cleaner. So for the other two questions, questions 14 and 12, I'm just going to set up what the region E looks like. Because after that, don't you just find this triple integral in these and off you go. And we've had plenty of practice at finding triple integrals. So I'm not going to do that. But here is 14. They tell me it's a I can't spell it, tetra, try again. Tetrahedron. There we go. And it's formed by this plane and x equals 0, y equals 0, and z equals 0. So that's essentially the region E. And the density function in this case happens to be 8y. So we're just going to set up what the limits of integration of this shape is going to be. Now, telling me it's a tetrahedron is actually quite helpful. Because if you find out where this surface, it's a plane I should say, where it cuts, don't you need to just know where it cuts here, here, and here? And won't that basically be your tetrahedron? Now, the plane is called x plus y plus z. If you want to know where it cuts the x-axis, don't you make those two 0 and the answer's 3? In fact, isn't the answer 3 for all of them? Now, we had a similar shape yesterday. If you take something, that dot's meant to be on the xy plane, and you go up and you hit this dot, won't this be on a sloping plane? So that is the range of z's. And so those are the guys I'm going to figure out first. Z starts at the ground, which is a z value of 0. And here, it's the equation of the plane. And all you do is rearrange it to be z equals. Are you happy about that? Now, what about the x and the y? And there's no particular reason why I wrote them in that order. Well, you got to just change your perspective. Isn't x and y going to come from the triangular bit in the floor? And if I rearrange that and orientate it the way we typically would, wouldn't this guy by 3, this guy here would be 3, and because the other guys are 0, isn't that my triangle?
Yeah, so therefore x can go from 0 to y, or y could go from 0 to x.
Yeah, I like this direction, so I'm just going to stick to the boring one. So won't x go from 0 to 3? And what will y go from? Well, 0. And won't the top part of y be the equation of this line, which I hope you can figure out is 3 minus x, because the slope's -1 and it passes through the y-axis at 3. So this is the region E. These are the limits of integration. So when I put the package together, and we'll start by setting up what the mass would look like. Which one goes in the inside integral? X, Y, or Z?
It would be Z.
Well, also called Z. What would the middle one be? What would the limit of integration of the middle one be?
X.
Are you sure?
No, it would
Okay,
be
good.
Y.
Yeah. Now, once I put 0 here and 3 minus x here, then the x's would go from 0 to 3. Now, if you're wondering what is the right order, if you look really carefully, isn't this one has to be first because it has all the other variables in it? And then doesn't the y guy have to be next because it's got an x in it? And doesn't the x have to be last because it's got numbers in it? Now, if you have two guys with numbers and one of them with variables, don't you put the variable one here on the inside? And if the other two are just from 0 to 1 and 1 to 1, can't you switch them and it don't matter? Right? But if there's variables in the limits of integration, you need to make sure that you do them in the right order. Otherwise, if you try and do the integration, you'll find out that you've got a letter left over, which you should never have. And that kind of means you're stuck. Okay, now that's the only piece of this puzzle I'm doing. But if you wanted to, couldn't you do the mx? Well, maybe I should do one of them. Which one do you want me to write the formula down for? X, Y, XZ, or YZ? Which one would you like me to just set it up?
X is odd.
X what? Which one of these?
Z.
Okay, XZ. So it's going to be the same triple integral. So these guys again, I'll just call them E. Y times 8y dz dy dx. Would you agree that the integration is almost the same question, right? That guy's just going to be 8y, this guy's going to be 8y squared. You're going to have an 8zy and you're going to have an 8xy. And they'll take 5-10 minutes to do them. Because they're slightly different, you have to do them from scratch. There isn't really a shortcut I can say. And then you plug them in here, here, and here, and you're done. And looking at this particular question, I don't see any symmetry. So I'm not sure I can see any way of, reducing your workload. But if you can set this up, would you agree the rest is just boring mechanics? Slightly different integral, all divided by whatever this comes to. And that's essentially all I want to do about 14. And the last one we're going to do is question 12. In question 12, you've got a shape, and I'll just write down the conditions. It's a lot of surfaces interacting with each other. So you've got this guy, you've got this guy, you've got this one, and you've got this one. And we need to set up what the limits of integration would be for each of these variables. And the density function happens to just be 7. Okay. Now you could try putting that into GeoBra and looking at it, but I think it would be so ugly. You'd be hard stretched to figure out what goes where, right? Pick any one of the 3 letters. Is there any one of those 3 you feel you could set up a limit of integration for, X, Y, or Z? I can see one that's kind of screaming out, right? 2 out of the 4 is screaming out, use me, use me. Who is it?
Let's see. So Z would just be 1.
Say that again.
So Z would just be going from 0 to 1.
What letter? Must be my hearing.
Z. Z.
Oh, Z. No, I wasn't, making you say Z there. I honestly couldn't pick it up for some reason. I think the mic or my hearing is losing that pitch. You think Z should go from 0 to 1, but Z goes from 1 minus y squared to 0. So where are you getting the 1 from?
Oh, I was thinking with different equations, but never mind.
Okay. I'm still going to use Z's. Can't I just say from 0 to 1 minus y squared?
Yeah, I got the one by like putting the y as 0, but I was like, oh, we are actually needing equations.
You put Z in the first equation. Can you get Y's lower bound as 1?
Yeah, later. You're right. But are we comfortable that those 2 guys basically tell me the Z bounds? Right, I'm going to use these 2 guys. I'm just going to rearrange them slightly differently. Would you agree if you rearrange that, it's this guy? Do you see the bounds on X? So 0 to 5 minus 5Z. Now, you were saying to me a minute ago, you should be able to get the bounds on Y, correct? And you said 1. That is correct. 1 is one of the bounds. If you take Z equals 1 minus y squared, and you use the fact that Z equals 0, so you imagine that you're drawing the shape like that. 1 minus looks like that. There's the 1, but isn't the other number negative 1? And so there you go. Now, could it be 0? Sure, but wouldn't they have to put y equals 0 here to make you do that? And there is no y equals 0 here. So we have to figure out what does that look like when z is 0, and it goes as a loop and the y values go from 1 to -1. So we have basically set up the bounds. So let's look at what the mass is going to be, the triple integral of that region, density function. Okay, who do you want? X, Y, or Z? Who goes in the inside?
It would either be X or Z.
Do you think it matters? Do you think X or Z? Do you think it matters if I do the X or I do the Z? What's your gut
You
feeling?
do
To do
the
the
X first.
Okay. And the reason you want to do the X is why?
Just since Z has the Y, which is the only one with where both limits are numbers.
So you're doing it that way, if I picked you up correctly, right? I don't think anybody's going to argue about the Y ones, right? Numbers go last, right? If you put that if that was the wrong way around, wouldn't you know when you got to the last integral because it'd be a Z left over or something that you couldn't handle, right? And so sometimes it can be a bit tricky which one, when there's variables involved in both of them, which one it is. If one of them has all the variables in it, right? If this was 5y take away 5z, it's definitely going first. But because this only has 1 and this only has 1, you could switch them and it could work, or you might have to do them in one particular order. In this case, it's going to be dx, dz, and dy. And from there onwards, isn't it just find the 3 different guys which will look just like this integral, but won't one of them have an x, one of them have a y, and the third one will have a z. So that'll make them a little bit, means you have to calculate them separately. There is no symmetry that I can see, so that's not really going to help as much. And that is the centre of mass. Any questions before we leave this and move on to what are called cylindrical coordinate system? Next guy is section 15.7. When you are doing an object in X, Y, Z, right, three-dimensional space, we have that guy, which is called Cartesian coordinates. Sometimes, haven't we done it, that you can use polar coordinates, especially if there's an x squared plus y squared and it's to do with the floor, right? We could do those. But there's another system called cylindrical coordinates. And there's one after that called spherical coordinates. Spherical coordinate systems are very good measurement system when you are dealing with planetary objects. Things in space that are moving in certain ways, typically elliptical orbits. They tend to become very nice equations when you write them down using a spherical coordinate system, and are really ugly equations if you try using X, Y, and Z, for instance. But what does a Cartesian one look like? Well, X is r cos theta, Y is r sin theta, and Z is Z.
Why exactly is Z just itself?
Well, essentially what you do to describe an object, say this piece here, is that you use polar to get that point there. So you imagine there's a circle and you tell me the angle and you tell me the radius, right? You tell me that's 5 and you tell me that's pi upon 6. And then once you get there, you just tell me the height is Z. And actually, haven't we done a couple of integrals where we did that, even though we never called it cylindrical coordinates? So if you got a question, just for argument's sake, if you got a question where the region was described like this, with some limits attached to it, we could do a triple integral doing that. But if I tried to do a triple integral doing that, wouldn't we end up with some really horrible equation? Because what you'd have to do is you'd have to say y was plus or minus the square root of 10 minus x squared. So can you imagine the limits of integration from negative 10 minus x squared to plus 10 minus x squared? It doesn't really matter what you put there. Can you imagine that's going to be one really ugly integral? Whereas if you convert it into polar coordinates, which directly is spherical, what do you do here? Well, won't that just become the radius between 0 and root 10, and theta becomes 0 and 2 pi? And won't z, let's say z is also, you're told it's 0, won't z just go from 0 to r cos theta plus r sin theta? And you see that would make a much prettier integral, especially if this function here had lots of x squared plus y squared stuff in it. Or even x squared plus y squared plus 2z stuff. It'd still be nicer to do, right? It'd be much easier to integrate things in cylindrical coordinates. So they have, I believe, one example of a conversion. So here goes. 0, -8, 4. And I would like to take x, y, z and turn it into r, theta, z. Right. The easy one is z. Agreed? Now, what about the x and y guy? Well, being a kind of visual person, I would draw our classic two-dimensional xy. I'd put a guy down here and call it -8. And then I would remember calc. Well, not even calc 2. Wouldn't I remember pre-calc 2 trig? And what would the r value be? And what would the theta value be? Okay, what's that angle? Because that's theta.
That would be 3 pi halves.
Oh, put it in the wrong place. And what would the radius of this circle be? And I put my little finish, maybe I should have put it there, but isn't the clue 8? And so,
2 root 2, or
just 8, just 8 in this case, right? Let's try another one. Suppose I gave you 2, -2, 5. And we want to turn it into cylindrical coordinates. The z is still 5. If I plot the point 2, -2, it ends up here. The angle theta is that angle, and r is the distance from here to here. Agreed? Now, from the origin to this point here, if you draw a little right angle triangle, any orientation you like, won't it be the square of 8, which is 2 root 2? So that would be an example where 2 root 2 would happen. Now, this angle here, the one I'm calling theta, you always measure from the x-axis and you go round anti-clockwise. That is actually a standard angle. Does anyone know what it would be? You could do the inverse tangent of y over x if you want a formula. What did you say again, Will?
It would be -45 degrees, which is just 360 times 40, so 315.
-45, -1/4, 7/4 pi, we always give the positive version. So when you tell someone the position of an object using cylindrical coordinates, you tell them on the xy plane that the radius is that and the angle you make is that. And then once you make that point, you then go vertically upwards, whatever z is. And wouldn't that give you the position of a point in 3D space? So how is that going to help us to find integrals? Well, some triple integrals are not very pretty, right? When you try and use x, y's, and z's, right? They have ugly square roots in them. So, let's do a little skill building exercise. How to convert z equals f of xy into z equals r's and theta's. Because very often what you're going to do here is you're going to get a surface and you're going to take the z formula, right? You know how it's like x squared plus y squared, plus z squared is 10, right? You've got that via theta, for instance, and you want to convert it into, say, z's. Right? Suppose I told you that x squared plus y squared minus z was equal to 9. Right, I have no idea what that surface looks like, but if I rearrange that surface, it should be x squared plus y squared minus 9, okay? you okay with me rearranging it? And that's what you got. Now, if you do x is r cos theta and y is r sin theta, and 9 is still 9, right? Remember to square it, you get z is r squared cos squared theta plus r squared sin squared theta, take away 9. Simplify that. What does that reduce into?
R squared minus 9.
Agreed? Now, can you imagine that might be helpful if you're doing limits of integration of a function, a surface? That if you just convert everything into r's and thetas, won't your triple integral become relatively nice? How about this fella? Z equals x plus y. Not really that much I can do this time. Are we cool with that? Now, let's make this question a little bit harder. Imagine that was z squared. Wouldn't my answer be the square root of that? And can we just assume that we know it's positive, because technically it could be negative. Even although that looks ugly, it will probably be a lot less work than working with this. Are we comfortable then that you can take equations like this and rearrange them as z equals something that uses r's and thetas? Don't you just make the x's r cos theta and the y's r sin theta? So here is our first question where we get to use cylindrical coordinate system. A triple integral over some region E, the square root of x squared plus y squared, the generic dv. And E is described as the region that lies inside x squared plus y squared equals 1 and between the planes z equals 0 and z equals 9. So from this, we are going to create r, theta, and z, right? Not x, y, and z, but limits of integration using r, theta, and z. I'm going to take the z one right out the bat. Would you agree that's a freebie? Now, inside the circle x squared plus 1 squared, doesn't that basically mean everybody inside a unit circle? And in that case, won't the r be between 0 and 1? And won't the theta be between 0 and 2 pi? Now, since they're all numbers, I guess it really doesn't matter too much what we do, but we'll set it up like this. This fella here needs to be converted into r's and thetas, right? The whole idea is get r's and thetas if you can. What will this become?
So when you convert the x squared plus y squared, you'll just end up with the square root of r squared, which is just r.
That's it. Now, normally this would be what dx, dy, dz. But when you do cylindrical coordinates, you get an r, dr, d theta, dz. You can switch them any order you like. Are you happy about where that extra little r is coming from? Remember polar, we had the same issue, right? So this is that guy, and that's why there's another r floating around. And in this question, I've just decided to do the r's first. And then I'm going to do the thetas second. And then I'm going to finish with the z's last. In this particular question, does it matter which order I do them in? Could I have done? No. Secondly, in this particular question, are the variables separable? So what I could do is the integral from z equals 0 to 9 of 1 times the integral of theta equals 0 to 2 pi of 1. And the integral from r equals 0 to 1 of r squared. And would you agree that that's a very easy set of integrals? Because boom, boom, boom. That would be 9, that would be 2 pi, and that would be a third. Actually, I should have said it, may as well do it. That ends up being 9. That ends up being 2 pi, and a third r cubed. That ends up being a third. So guess what? The answer is 6 pi. Now, if we had left that question and tried to deal with that same problem, wouldn't we have some really ugly limits of integration for the x's and y's? X would go from -1 to 1, but wouldn't the y go from negative the square root of x squared plus y squared minus 1 to positive the thing? And I'm not even sure that integral is doable. So
Yeah,
cylindrical.
that looks like a burn it with fire integral.
I'm not sure of that context, Terence.
If something's really bad, you get a
Oh.
flamethrower and you burn it with fire.
Okay,
That's like,
I gotcha.
how do you kill the plague? You burn it with fire.
Gotcha. Or kill all the rats. No, kill all the cats, even though it was the rats that were actually had the fleas that were giving you the plague. So be careful when government tell you that they know the science. At least in the medieval days, they weren't very good at it. Right. Let's set up for z equals x squared plus y squared and z equals 4. So you've got a plane called z equals x squared. I think that's actually an upturned, is it upturned? Yes. It looks something like this. And z equals 4, wouldn't that just be basically a flat plane parallel to the xy plane? So this is the guy we're going to get the triple integral for, but we are going to do it using cylindrical coordinates. So I need to figure out, I need to figure out what r is, what theta is, and what z is. Well, there doesn't seem to be an awful lot of information there, but if you put the information together, isn't 4 x squared plus y squared going to be the intersection of this surface with that plane? Oh,
Yes, which means our radius would therefore be 2.
and the whole circle, because there's no indication anything is going on. Now, z is a little bit tricky, but not that tricky. Doesn't it have this guy and this guy? So wouldn't that be from 4 to r squared? Are we good? I just had a thought. Couldn't it be r squared to 4? So I'm reading the question now. Evaluate this integral when it's a paraboloid and a plane. So the paraboloid is first and the plane is second. Okay, that goes first, that goes second. If I get it wrong, won't the sign just be negative when it should be positive?
Or positive when it should be negative, one of the two.
Whatever it is. So, you know, if the first one don't work, can't you just pick the other one and it'll be fine, right? So our setting up our integral then is this guy. And it's going to become Okay, what will we do? Well, we're going to have a Z. Right. I have three different guys. Who goes in the inside?
It would have to be the r squared to 4.
Right? So that's going to be from Z equals R squared to Z equals 4. And I'll do a dz here. Actually, I'll do my r dr d theta at that side. It kind of makes more sense there, doesn't it? Right. What about the other two? Aren't they going to be r and theta? Can I switch them any order I like? Yeah, they're both numbers. So no particular reason. 0 to 2 and 0 to 2 pi. Now, do you see in this case, the Z is there, but the Z's not a problem because isn't it going to disappear in a minute? Because what we're going to be able to do is integrate that, which is a half Z squared, evaluated at Z equals R squared to Z equals 4, and then we'll do the other two variables after that. If you plug in 4, you get 16, and a half of 16 is 8. Take away 1/2 r to the 4, r dr d theta. And that's going to go from r equals 0 to 2. Do you see everything's fine now? Won't it just be integrated with r and then finally integrate with theta? Agreed. Now, if I was really thinking about it, although I couldn't separate it when we did the triple integral, could I separate this double integral? Are the variables separable? Yeah. I would get a 0 to 2 pi of 1, and an integral from 0 to 2. Remember to multiply everybody by r. Right, at that point, would you agree it's just calculus 2 and do your thing and call it good? Right. I've got while I'm doing this, you can put down your last name for attendance because I want to show you something. This darn thing would load up, which I have. Right. Okay. Well, hopefully you've all done that by now. You know that the midterm is on Monday. Are you looking at our canvas? Right.
Yes, I can see Canvas.
Right. So if you click on midterm exam information, you click on that guy and it will tell you a little bit about the test, how long it's going to last, when it's happening, and all that good stuff, in case you've forgotten. It will also tell you that we are going to have 10 multiple choice and 10 section 2 questions. That's what I'm going to design it. Right, now the multiple choice questions, right, you get a question and there's 4 answers, you pick the right one. I do not want to or even need to see working for those. All you're going to do is say question 1 is C, question 2 is D, okay? And then the section 2 questions, you're going to show me all your working. So nothing is going to be on WebAssign at all. You are allowed to use Desmos, GeoBra, things like that, and they're actually here for you. Everything else in Canvas will disappear, and everything in WebAssign will disappear during that day. And click on this guy, hopefully it'll work. This is the Zoom meeting that you will use to come into the test, right? The midterm exam, right? It's not your class one, it's that one. Here is a practice one. You never know with these things. I'll click on it, see if it opens up. There we go. So what I've done here is just put together some questions from previous tests that I've done, previous exams, and it's just not cooperating. Right, go into student view. I don't know why it does that. It just been a pain in the butt. Right, try it again. There we go. In student view, it looks like it's going to load up. eventually. There we go. So here are examples of some of the types of questions that you could get. And here are the solutions.
So I saw that there was a link to something called Microsoft Lens. I actually have a different scanner app on my phone. Is that okay?
Totally fine with that. Right. So if I just get close this. So that's just a resource. You can choose to use it or not. What else I have in this is, let's talk about it. You have to take pictures of your working and turn them into PDF. I'm using Microsoft Lens, but if you have a CAM scanner or you just use your printer scanner or whatever it is you use, as long as you get it. If you're not done it before, this is a little dummy one that you can just practice uploading. Right, so if I click on this fella, and I think I have to go into student view because there. Start assignment. You've saved it to OneDrive or you've saved it somewhere else, right? On your phone, on your computer. Choose file. Pick whoever the file is, make sure it's a PDF. Open it off and submit assignment. That's all you need to do. Now, if you use Microsoft Lens, try and put them all together. You're allowed to, take 8 pictures and then combine them into one. And that makes my life easier. Doesn't make your life easier, but it makes my life easier. And since I have to grade over 100 of these darn things, because of 5 classes, it's more like 150 of them. Anything that saves me having to go through 7 separate pages and load them up and check them does help a lot. So try and figure out how to make that happen. Yes.
What time is the midterm?
There's a window. Our midterms are going to be either 10 till 12 or 11 till 1. You pick whatever 2 or time slot suits you best. Okay. If those time slots don't work for you, then we have a little conversation and we figure out when it's going to be. Based on other things that have happened, it's probably going to be at 7 p.m. on Monday. And you will do it then. Hopefully you're free at that time slot. But the best time slots are the ones near to your class, right? So 10 till 12 or 12, not 10. Yeah, 10 till 12. Yeah, that works. Or 11 till 1. I think I've got GeoBra here. I've got Desmos. That will be there. If it isn't inside midterm exam, it will disappear. You won't be able to see it during the exam. Any questions before we call this a day? Because it's been a long day, hasn't it? Well, you can always ask me tomorrow or see me during office hours. Bye-bye for now, guys. Have a nice break. See you tomorrow.
Thank you. Have a great day.
Bye-bye. Tim, bye-bye.